Okay, let's go through the answers to these questions. So, first one shows you a diagram of a plug, and it asks you to identify the wires. So, the live is always connected to the fuse, so it is C. The neutral pin is on the opposite side to that, so it's A, and then the earth pin is the green and yellow striped one at the top. Okay. What names are given to the parts? Label D and E. D is the fuse and E is the cable grip. Okay, so it kind of grabs on to the cable, so if someone kind of trips on the wire, it doesn't pull out. Next one, and it is a good question, it does tend to turn up every so often, and there's a chance it could turn up on a test that you do. So it says a washing machine has a metal frame. A fault occurs so that the live wire connects to the motor, is detached and connects with the metal frame instead. Explain fully how the fuse and the earth wire in the plug above work together to prevent a person touching the frame being electrocuted. Now your answer could be very different than mine, but it has to kind of probably hit on a few key points. So I've said the earth wire is connected to the metal frame. I think that's your first mark, because it has to be of any use in this purpose. And it provides an alternative path for the current to travel through. I just realized I missed out a word there. Let's fill that in. And provides an alternative path for the current to travel through. Now, rather than going through the motor, the current is just going between the live wire, the metal frame, and the earth wire. There's very little resistance there, so that decreases the resistance, which means the current increases. That increase in current will exceed the fuse rating. So the wire in the fuse will then heat up, melt, and break. And that then isolates the person from the live wire, rendering it completely safe. Okay, so those three key things. Earth wire is connected to the metal frame, provides an alternative path. The path now has less resistance, so the current goes up. And then the current going up causes the fuse to blow. Okay, so those things working in conjunction with each other make it safe. Next one is a paying for electricity question. So it shows you the meter readings at the end of each week. And you have to work out, fill in a few boxes here. Now, if we look, the gap between each of these readings, okay, so if you look at the reading from the previous week and subtract it from the current week, that tells us how much electricity has been used during that week. So for this one here, we have to do 12556 minus the 12399, and that gives us 157. We use 144 in this week, so we have to add that on, which gives us 12681 plus 144, which is 12825. What do the units in the table above measure? So it's the number of units of electricity, but that is just the energy that has been used. Electricity costs 11 pence per unit, but 1 unit of electrical energy is equal to 1 kilowatt hour. So therefore this is very simple, and you can see there's no working out because with 1 mark there's no space to do any working out. It is just 11 pence. Because of the same thing. 11p per unit means it'll be 11p per kilowatt hour. Calculate the total cost of electricity in Mrs. Henderson's home in week 2. You're advised to show clearly how you get your answer. So the units used in week 2 actually go under week 3, because we can't tell that until week 3 starts. So it's 129. So we do 129 units multiplied by the 11 pence gives us 1397. However, that's pence. We need to divide that by 100 to get it into pounds. So 13.97 pounds. Okay, next one. The mains electricity used in our homes has a voltage of 240 volts. It's usually somewhere between 230 and 240, so the question will tell you what to use. A food mixer uses a current of 2.5 amps. Calculate the power. The equation we're going to use is P equals IV. So we just multiply the current and the voltage together, and that gives us a power of 600 watts. An electric drill is also operated from the mains and has a power of 950. Calculate the correct fuse. So to do that, we need to work out what current it will draw. So it's 950 watts of power, and the voltage we've been told is 240. So rearranging that, dividing by the 240, tells us that the current is going to be 3.96 amps. Now, there's no such thing as a 3.96 amp fuse. We always use the one that's above that, but just above it. So in this case, out of the options we've been given, it is a 5 amp fuse that we would use. Okay. Mr. Henderson is an electrician. He wires an electric heater up to the main supply. The incomplete circuit is shown below. Live wire usually goes straight into the fuse. Then we have a switch, and the very last thing is the heater. Okay, so from starting at the live and going around, it should be fuse and then switch. Now sometimes there's a fuse switch in the kind of wall and then a fuse, so you can sometimes see those two the opposite way around, but both those must be before the heater, whatever component it is that we're using, or whatever appliance it is that we're using. Okay. So placing the switch in the wrong position in the main circuit is dangerous. Explain why this is so. Because if the switch is placed between the components in the neutral terminal, the component will still be connected to the live wire even when the switch is open. So let's say we did do this wrong and we change this switch to here. And there's our heater, and something goes wrong with our heater, so we want to fix it. So we come along to our heater, and we're not stupid, so we open the switch first. And that might make us think that's safe to touch. And had those been placed the right way round, it would. But if you look now, this heater is still connected to the live. Remember, it's the live that provides all the voltage that pushes the stuff around, the current around the circuit. Therefore, you could still get an electric shock from this. So we need to make sure that these are placed correctly. So then, if you go to fix the heater now, and the switch is open, got very long arms, there's no connection from you round to the live. Okay, you're only connected to the neutral, and the neutral's at 0 volts, so it's completely safe. Okay. So say if the switch is placed between the component and the neutral terminal, the component will be connected to the live wire even when the switch is open. And lastly then, question involving our two-way switches. We sometimes call these a double switch, but in the mark scheme it says it's a two-way switch, and we should stick with their wording. Where would you use such a circuit in the home? The most common place is the top and bottom of a flight of stairs. Describe briefly the advantage of the homeowner. The bulb can be turned on and off from 2 locations. Okay, so at the minute that bulb is on because you can take that path around the circuit. However, it doesn't matter which one of these switches, A or B, I move. If I move A to here, that turns it off, and if I do the opposite and move B, well, that also turns it off, so it can be controlled from either of those positions. On the circuit diagram, mark with the letter F a suitable location from the fuse. Sorry, moving on to question 5 too early there. On the circuit diagram, mark with the letter L the live terminal of the supply. The component that we're interested in, okay, the appliance should always be next to the neutral. The switch should be between that and the live, so that will be the live, and then we would probably put the fuse before the switch there. So there's our fuse. Okay.